Okay. Now it's working, I hope. Yeah, so hi. Thank you for the introduction, Henry. I'm Wenke. In the large scale structures group, and I'm working on disurfactant mixtures. My supervisor at the ILL is Ralph Schwartz. And I'm mostly working with small angle scattering. But this talk today will be a little bit more different since it's about neutron interferometry. And with this, I would really like to start my presentation. So, yeah, interferometry in general is something that most of you should be familiar with, and particularly visible light interferometry finds many applications in our everyday life. So we all know, for example, the Michelson interferometer in IR spectroscopy. And in addition to that, interferometry is used in astronomical telescope or to measure surface roughness. Neutron interferometry, however, is a bit more special and actually permits us to talk about cats again. In fact, neutron interferometry is an important tool for the realization of many textbook experiments in quantum mechanics. However, it also allows for some more pragmatic measurements, such as the determination of scattering length. During this talk, I will first give a short, somewhat general introduction about neutron interferometry in detail, and then I will talk about the determination of coherent scattering length and about some experiments for the observation of quantum mechanical phenomena. Finally, I will then talk a bit about the instrument setup and subsequently conclude my presentation. But first of all, a short recap. So what actually is interferometry? So basically, as the name suggests, with interferometry, we use interferences which arise due to the superposition of waves to extract information. And for this purpose, an incident ray is split at a single point into two rays that follow separate paths. And after having interacted with a sample or not having interacted with a sample, the split beams then converge in a single point, in which the beams are then recombined with constructed and destructive summing of their amplitudes. And then the squared magnitude of the summed amplitudes produces a modulated intensity pattern that is characteristic for this phase shift introduced here. The picture I now used for the explanation is the Mach-Zehnder type interferometer, and it's based on the division of amplitudes as it's shown in the picture. Another type of interferometer that you may know is the Young type interferometer, and it's based on the division of wavefronts. And in fact, the first neutron interferometer was based on wavefront division, but it had several constraints for interferometric application, mainly due to the very small separation of the beam paths of about 100 micrometer. So in the end, another approach for neutron interferometry had to be found. And this is based on the division of amplitude interferometer. However, the development of a division of amplitude interferometer for neutrons comes with some obstacles compared to visible light interferometry. And the most important one here is the lack of suitable mirrors. As you may know, neutron refractive indices of most materials are a bit smaller but close to 1, which allows for total reflection only for grazing incident angles, as it's shown here. A grazing incident angle, in case you don't know the word, is an angle of almost 90 degrees from the surface normal, which is very close to the surface. This produces only a very small beam separation, but in order to place a sample somewhere, like in only one of the beams, a large beam separation is needed. And this problem was overcome by the development of a perfect silicon crystal interferometer in 1974. It is based on Bragg diffraction, Lauer diffraction of an incident neutron beam, and part of it being transmitted, part of it being reflected by the crystal lattice plane. And as the name suggests, a perfect silicon crystal interferometer, it is fabricated from one perfect silicon crystal by cutting out some parts and leaving 3 slabs with equal spacing in between each other. And I'm going to talk about a bit more about this interferometer in the next slide and compare it to the visible light interferometer. So we start with the incident beam, which is light here, which is neutrons here. And this one is then incident on the first slab at an angle. The beam then gets partly transmitted and partly reflected, giving rise to 2 beam paths as shown here. Let's call the red one path 1 and the purple one path 2. The second slab then acts as a mirror, here compared to the Mersenne type interferometer for visible light. It reflects both of the beams. Of course, a part of them is transmitted as well, but this is not relevant for our experiment now. The last slab is then called the analyzer and leads to the partial reflection and transmission of both beams. And during interferometry experiments, usually two detectors are used, the O-beam or forward detector and the H-beam or deviated beam detector. So let's now have a look on the intensities that are detected on each detector. So first of all, Serena already gave some similar function in her talk. The intensity on any detector can be calculated from the amplitude of the interfering rays from path 1 and path 2. And for this calculation, actually, the path which the neutron ray has taken becomes relevant. That's why I stressed it in the previous slide. So the O detector, shown here, as I said, detects the forward beam. And as shown on the previous slides, in order to reach the O detector, the wave from path 1 gets transmitted, reflected, and then reflected again, which gives rise to these coefficient T, RR, where T is transmission and R stands for reflection. The wave from path 2, however, also gets reflected twice and transmitted once. That means that the amplitude and the phase of the wave function in the forward direction behind the empty interferometer are composed of equal parts coming from path 1 and path 2. So to explain it a little further, psi1 is the incident wave function, which is the same for both paths since they are derived from the same incident beam. However, and this is given here, the phases of the waves in both beams may become different when the neutron experiences an interaction along the beam path, which is expressed by the contribution psi. And since we're dealing with interferometry, we are interested in the intensity modulation arising from the phase difference between the waves of both beam paths, which is given by this equation. And in the ideal case, the intensity pattern for the O interferogram displays complete modulation according to this cosine equation. I will talk about how we achieve this phase shift in the next slide. Let me just give some notes on how the intensities detected on the O and the H detector relate. So obviously, the intensity of the neutron beam at the H or deviated beam detector is different from that of the O detector. And most strikingly, it's inverted in phase compared to the O detector, which is due to the odd number of reflections and can be expressed, with a minus sign in front of the cosine term. So you've seen it shortly now, but if you plot the intensity on both detectors as a function of the phase difference in between the wave of the two different paths, it looks something like this. And what more is important here is that particle conservation exists, and that's why you see this formula. So the sum of the intensities of both beams needs to be constant. And in addition to that, silicon has essentially zero absorption for thermal neutrons, which is very advantageous for manufacturing interferometers out of silicon perfect crystals. So now about the important question, how to vary the phase difference to get these interferograms. And basically, it's quite simple. We just need to place an obstacle for the neutron somewhere in the neutron beam, or here, as shown here, in both neutron beams. And this is done by inserting a so-called phase shifter, which is often nothing more than just an aluminium slab. And when the slab is rotated, the neutron beams on both paths move through different path lengths within the slab. And the difference between these path lengths in the slab for the different neutron beams can easily be calculated from the thickness of the slab, from this angle of rotation here, and from the incident angle, and is given by this equation. However, for calculating the interference pattern on the detector itself, we do not need the difference in path lengths, but rather the phase difference between these two paths. And this can also quite easily be calculated by knowing the refractive index of the phase shifter, which is inserted, which is aluminium in this case. And then finally, we can detect an intensity following a sinusoidal relationship on the O detector, somehow in accordance to this equation. So As you may notice, this is slightly different from the ideal equation I showed before, in terms that it includes experimental imperfections. Hence, intensity oscillations are somewhat damped compared to the predicted behavior, and this is mostly due to imperfections of the apparatus, especially the interferometer itself, and the neutron beam being not perfectly monochromatic. To explain a little further, C here is the mean counting rate in one of the interfering beams and includes the non-interfering background. And delta psi, as I said, is the phase shift. And phi is an internal phase shift of the interferometer itself and has to be measured for data reduction. So, to summarize, rotating the aluminium slab creates a phase shift between the two neutron waves, which then interfere behind the interferometer. And you may ask yourself, okay, but why is she giving all of these equations? Why can't she just explain it in a more general and non-quantitative way? So, well, these equations are actually quite important for one of the most relatable applications of neutron interferometry, which is the determination of coherent scattering length. And as you may infer from this equation, if you know the difference of the path length, and if you know the interference pattern, you are able to calculate the refractive index of a material, which is first under some assumptions, for example, if you don't have very strongly absorbing materials, related to the coherent forward scattering length of a material by this equation. And particularly in soft matter, reliable values for coherent forward scattering lengths are needed. So what is done is to record an interference pattern as a function of the path length difference between the two neutron beams by simply inserting a sample. So for example, we can take the sample instead of the phase shifter, and then from that, calculating the refractive index and knowing the number density or the particle density in the sample, we can then get the coherent scattering length of the nucleus we're interested in. And this very easy approach that I just described is, as I said, just done by changing this phase shifter for the sample, and it's called conventional method. The relative error in the coherent scattering length is usually in the order of several parts of 1,000, and is determined by how accurately the period of the oscillation can be determined from the interference pattern. Also, there are several other sources of error here, for example, sample thickness, the mean wavelength, and the sample orientation as well. And actually, there are two more methods which give probably more reliable results in terms of the neutron refractive index and the coherent scattering length. I won't go too much into detail here, but one of them is the standard sweep method. And this is different in terms that an auxiliary phase shifter is used and the sample is inserted in one of the beams here. And what is done during the standard sweep method is to alternatingly insert the sample and get it out of the beam again in order to simultaneously measure not only the sample, but also like the background and most importantly, the internal phase shift of the interferometer itself. So that reduces the error due to the so-called internal phase drift, which can arise due to fluctuations in temperature during the measurement, or also vibrations of the optical bench. And finally, there exists another interesting method called non-dispersive measuring method. And it looks simple to the standard sweep method, only that the boundary of the sample is oriented parallel to the reflecting planes of the perfect silicon crystal. And from some simple geometrical considerations and Braggs law, the phase shift, for which the formula is shown here, then becomes independent of the neutron wavelength and only dependent on the well-known lattice plane spacing of the interferometer perfect crystal. And of course, the advantage here is obvious. The necessity of a precise wavelength determination is eliminated, and when one can use an incident beam with a broader wavelength spectrum. So, That's it about measuring the coherent scattering length. However, the determination of coherent scattering length nowadays is not the main area of application for neutron interferometry. And from my talk to Hartmut, I got that the last measurement of such a kind was carried out about 8 years ago at the ILL. So nowadays, much more interesting experiments are carried out, mostly to study the foundations of quantum mechanics. And this is what the first example is all about. So this first example is a very historical one and shows the 4-pi symmetry of the spin 1/2 wave function. And just to tell you what we're going to prove here, the 4-pi symmetry of a spinor wave function is a common feature of all spin 1/2 particles. And if you know a lot about quantum mechanics, this may be very fundamental to you. However, if you have, just as me, only a very elementary understanding of quantum mechanics, you may understand what 4-pi symmetry of a wave means, or what is a spin 1/2 particle, but you may not know the term spinor. And just to explain it in one sentence, spinors are mathematical tools that allow us to describe the quantum rotation of fermions. For example, during the Lamarck precession of the fermion magnetic moment in a magnetic field. And this quantum rotation is shown here and can be portrayed as a function of the Lamarck precession angle alpha. So here, the polarization vector of the neutrons, which is displayed with the arrow, returns back to its initial state after a 2-pi rotation, and then of course again after another 2-pi rotation, being 4-pi. However, the neutron wave function itself is antisymmetric with respect to a 2-pi rotation, as it's shown with the color here a bit. But it shows 4-pi symmetry. And yeah, so the neutron wave function at 0 Lamarck precession angle first has its initial value as antisymmetric in phase after 2-pi rotation and only returns back to its initial value after a 4-pi rotation. And as shown below with the intensities, this behavior cannot be measured or observed by only measuring the intensities. And even though this behavior was kind of known at an early stage of quantum theory, it was considered to be inaccessible by measurements until they found out about neutron interferometry. And the possibility of this kind of measurement was actually predicted as soon as the neutron perfect crystal interferometer was developed. And 8 years later, in 1975, an experiment was actually done. And yeah, the experiment setup is actually kind of simple. You only have the perfect crystal interferometer, and an electromagnet creates a constant magnetic field which is introduced to one of the beam paths. And the interference pattern observed behind the interferometer is given by this equation and actually only depends on the Lamarck precession angle alpha. And then the Lamarck precession angle alpha can actually be calculated by the strength of the magnetic field we're applying and the neutron's trajectory within the magnet. So we can actually kind of precisely determine the precession angle alpha and also measure the intensity detected at a detector as a function of this precession angle. And such an interferogram is shown here. And what was then done was to observe, okay, how long is the period of such an observed oscillation? And it was found that one period was completed after precession angle of alpha being 715 plus minus 4 degree, which almost corresponds to 720 degree, which corresponds then to a 4-pi rotation. So this was one very, very fundamental experiment and carried out quite some time ago. But also nowadays, there are more current examples and very, very interesting examples of experiments which are carried out at the Neutron Interferometer. So let's move on to such an example. The Cheshire Cat. The ones of you who know Alice in Wonderland may know that there's a cat that can vanish but leave its smile behind. And this cat is called Cheshire Cat, and it exists in quantum mechanics as well. The term quantum Cheshire Cat refers to an object whose properties can be separated from its physical location so that the two can be measured at different places. And it sounds weird, but we have to keep in mind it's quantum mechanics. And what I would like to mention at this point that this experiment exploits a very important principle in neutron interferometry called single particle interference. So based on the intensities available at any kind of neutron source, there's on average only one neutron at a time within the interferometer. And this means that the two paths I showed you before in the interferometer setup are taken by one and the same neutron using its wave function to describe the phenomenon. And to detect the quantum Cheshire Cat for neutron, an experiment was designed to get a neutron travel along a different path from its spin, to say it in simple words. And actually, the design of this experiment is shown here, and it seems to be very complex, but it also shows many components that can be used to design an interferometry experiments. So that's why I would like to explain to you the experimental setup. So let's start on the left. First of all, a polarized neutron beam was used, which is achieved by using a neutron polarizer portrayed as this gray box here. By the way, the whole setup is surrounded by a magnetic guide field to prevent depolarization. Then we have a spin turner here, which rotates the polarized neutrons by 90 degrees before they enter the perfect single crystal interferometer. The spins in path 1, or like here, the path 1 is the lower part of the experiments, are then rotated by the spin rotators to have a direction anti-parallel to the neutron's direction of light, which is indicated with this black arrow here. However, the neutrons in the upper part are rotated to have a spin direction parallel to the neutron's direction of light. For the moment, we will just ignore the absorber, which is in here. It will become important later. And as for all the interferometry experiments, the intensity of the final neutron beam behind the analyzer crystal is, of course, observed as a function of the phase shift between the different paths. And the phase shift, again, is achieved by rotating a phase shifter. What is special about this experiment compared to other experiments is that there's a spin analyzer in front of the O detector here. And this spin analyzer only needs neutrons path, which had a spin parallel to the neutron's direction of light, meaning they took the upper part before passing the second spin turner shown here. This means that the O detector should in principle only detect neutrons from the upper path if there's no additional polarization introduced. And we have the H detector as well, and the H detector detects neutrons with all spin polarizations. So, but how can we be sure that the O detector only detects neutrons taking the upper path? This can be verified by investigating the effect of adding an absorber to the different beam paths. And what I would like to mention first here is, since the neutron spins of both paths are polarized in opposite directions and have therefore no orthogonal component, no interference pattern should be visible. And this seems to be the case for all measurements here. To find out which path is detected, either the lower one or the upper one, an absorber is then inserted either into the lower beam or in the upper beam, as shown here, and the detected intensity is compared to the measurement without the absorber, which is shown in the middle. And please note that we're only looking at the O detector for now, which has the spin analyzer in front of it. So inserting the absorber into the lower path changes nothing about the intensity, which suggests that neutrons from the upper path are detected. This can be verified by inserting the absorber into the upper path, and indeed the detected intensity is lower. This confirms that only neutrons taking the upper path are detected here. And again, this is the case because they have a spin parallel to the direction of travel, and which pass the analyzer then, as opposed to the neutrons taking the lower path. So, after having established that, we want to see which path is sensitive to spin manipulation. And first of all, shown here, the spin is essentially the grin of the Cheshire Cat. And this experiment is a little bit more tricky. And we have to look at both detectors here. And that's why the first line here shows the H detector signal, whereas the second line shows the O detector signal. And for the purpose of finding out which path is sensitive to spin manipulation, the direction of neutron spin was changed a little bit, using an additional magnetic field either in the lower or in the upper path, as shown here. But first, let's have a look again at the case where no additional magnetic field was introduced to change the direction of neutron spin. And again, neutrons taking the upper path are polarized in the direction of travel of the neutrons, and the ones taking the lower path in the opposite direction. And of course, as seen before also, here's no interference pattern visible on either of the detectors. And just note that the H detector has no spin analyzer in front of it, which makes it possible to detect all the neutrons regardless of their spin. And again, there's no interference pattern because of the non-existence of an orthogonal component of the neutron spin. By rotating the neutron spin a little, however, an orthogonal component is introduced, and this also introduces the possibility for the neutron beams of the two paths to interfere with each other, as it is shown here when the neutron spin of the lower beam path is rotated a little bit. And that means that the spin of the neutron in the lower path now also contains a component parallel to the neutron's direction of light, which can be detected by both detectors, which is seen here. If the same is done for the upper path, however, the O detector shows almost no oscillations anymore, whereas the H detector shows a clear intensity modulation. This means that no interference of the spin component parallel of the direction of light of the neutrons can be detected if the spin direction in the upper path is deviated a little bit with a magnetic field. And this experiment basically shows that only the lower path here is sensitive to spin manipulation. And just for you to recall, the neutron on the opposite was detected in the upper path as shown in the previous slide. So that's what the quantum Cheshire Cat looks like, and this is kind of a pretty recent experiment. Of course, there are many more examples of what can be measured with neutron interferometry, mostly in the field of quantum mechanics, but not limited to it. And to quote Helmut Rauch, one of the most important researchers in neutron interferometry, neutron interferometry has become an important tool for the realization of many textbook experiments in quantum mechanics. If you want to learn a little bit more about interferometry experiments, I've given two sources here, but I won't go into detail due to limited time. On the end of my presentation, I would just like to give a little overview about the ILL instrument, or better CRG instrument S18 at the ILL. It is a collaborative research group instrument of the Technical University of Wien, and actually very easy to find since it's the first instrument when entering ILL7 from ILL4. And what is very special about the whole instrument is that it's well isolated in terms of vibration and temperature, since interferometry experiments are very sensitive to these disturbances. So also the perfect silicon crystal here is located on a vibration isolated optical bench. Also, the stable temperature is ensured by two housings around the whole setup, and thermostats are used to keep the temperature of the whole setup constant. S18 uses thermal neutrons from the beamline H25, and here the neutrons are first selected by a monochromator. And as shown in the Cheshire Cat examples, the neutron can then be polarized and spin flipped if needed. The position of the neutron interferometer together with the phase shifter is indicated as well. And also the existence of the detectors, the O detector and the H detector, should not be something new to you. By the way, the neutron interferometer is, by the way, not limited to this very strict E-shape that I've shown before. The choice of the interferometry geometry is mostly based on the size of the sample. And what is interesting about the S18 instrument as well is that Uson's measurements can be performed here, which means small angle scattering measurements at very, very low Q. So, having also talked about the setup now, I would like to conclude my talk. Neutron interferometry, just as visible light interferometry, exploits the phenomenon of interference to extract information. Currently used neutron interferometers are based on the division of amplitude and consist of a perfect silicon crystal, which separates the incident neutron beam by transmission and Bragg reflection. In interferometry experiments, the intensity on one or two detectors is measured as a function of the phase shift in between the two paths that the neutrons can take. And this does not only allow for the determination of neutron refractive indices, but also gives rise to many possible experiments related to quantum mechanics. In this talk, I gave the example of a rather fundamental historical experiment proving the 4-pi symmetry of the spinor wave function, as well as the Cheshire Cat. Finally, I gave a small overview about the S18 instrument setup. And with these words, I would very kindly like to thank you for your attention, and many thanks particularly to Hartmut and Armin, who helped me a lot with the presentation.
Okay, well,